All right, so today is one of the lectures that, oddly enough, in the first class I got pretty riled up on. So usually it's one of the driest lectures. It's about the UML, the Unified Modeling Language. All right, and it is fairly dry, and it would help if I turn on the slides there. All right. And one of the reasons why is because today is not so much about, it's about this problem that's totally understandable to have right now. When you're given a homework assignment, if you're like me, then more than likely, this is what you do. You go home, or the first thing you do is you open up your computer, and you open up an IDE, and you start typing, right? It's totally understandable. Unless it's just like an issue of scale, we might think about it before we start typing, but one of the first things that we generally tend to do is we generally tend to start typing. And right now, at this point in your career, it's likely that you haven't seen anything to the scale where you've needed to do otherwise. UML is about the design and conceptualization of systems. It's a way to sort of break down and specify complex systems before we start creating them, all right? And for that reason, it's worth talking about because it's another way that we can mature as software developers. So the UML, and I know I say it that way, the Unified Modeling, and I know it sounds weird, but it's kind of like you wouldn't say the HTML, but the UML is the Unified Modeling Language. And it was created as a standard by the three amigos of software engineering. They are Booch, Rumbaugh, and Jacobson, or Jacobson, depending on where he's speaking at the time. And my story about these is that in 2007, I went to the International Conference on Software Engineering. It was in Minneapolis, Minnesota, and I had my biggest fangirl moment of walking in an elevator, and Grady Booch got onto the elevator with me. He's like this tall, super long gray hair, really big belly, and I was like, hey. I couldn't manage a question or any other conversation. I just couldn't get it all out. They're really huge because they're in some ways called the fathers of software engineering because of their work on software design. And it's their work that created the meat and the vast majority of the Unified Modeling Language. Now, the reason why this can be a little dry is because this language is purely about the creation of design documents, just the documents. And that's why it can be a little tough to get through, because that's not an exciting thing to go home and say that you did, is I learned how to make documents today. It doesn't feel like it's even computer science, but these documents are incredibly useful, especially when we talk about object-oriented design. The reason why is we're going to see that some of these documents have a one-to-one relationship with code, which is really, really cool when you start to think about it. Now, the thing about it is that it's not a process, meaning that it's not something that is a new software design process. Instead, these documents are used in other software design processes, things like Agile, Waterfall. Now, there have been approaches that are purely based on UML. If you've ever heard of Rational Roads from IBM, this was an example of one design system that was supposed to just make it to where all you did was click and point and you got software at the end of it. But this is not what we're talking about, but this is one of the biggest features that I will say over and over and over again about UML. It doesn't matter what language you're writing in, UML works. Now, all of you have seen multiple languages, but some perfect examples of really hyper object-oriented programming languages would be Java, C++, C#. And I think all of you have seen those languages to some degree. And these documents that we create, it doesn't matter what you're creating in. It can be any of those languages. The UML doesn't care, all right? And we're actually going to see this taken to a next level pretty soon. So why do we use it? Well, first off, it's a standard. If you read another way to do this on the internet, ignore it. I mean, some cranky nerd got tired of doing something other ways, right? This is a standard. There's only one way, which is really one great thing about UML. The other thing is that this is relevant throughout the entire life cycle, regardless of what life cycle you follow. one of the diagrams that we're going to talk about is going to be useful from the very first point of a software. Like, oh, I'm going to do this. Okay, I'm going to start building this diagram. And that diagram is going to stay relevant and central all the way to deployment. I said that right, all the way to deployment, this one diagram is going to be relevant. It also is graphical in nature. So we're not talking about code. We're not going to be writing an IDEs today. And one of the things is our customers do tend to be smart people. And this is the way that we can communicate with customers. We can communicate with users in a way that's sort of comfortable to them. All right, so yeah, that's enough. So I'm going to show you slide 4, but I want slide 4 I want something to be clear. I don't care about anything on here other than one sort of general thing. There were lots and lots of standards. And at the bottom of this slide, there's lots of things. So around 96, 97, they all got consolidated, which is why we use the word unified there. There's only one. It used to be there were options. Now there's only one. And that's since 1997. That was before quite a few of the people in this room have been born, right? So it's significant that we've had a unified version. The only thing that's important from this, don't you dare study this slide for an exam thinking I'm going to ask, when did UML 1.1 come? No. All right. What matters is it's been unified for a very long time. All right. So before we get into our first 2 diagrams that we're going to cover today, let's talk about some vocabulary words. And they are systems, models, and views. And I'm going to use an example of this that has nothing to do with software because it is important that we disconnect the concepts from the code that we're going to be creating. And first off, what is a system? A system is the thing that we are creating, right? So inside of software, it might be something like a student advising portal. But in maybe a different example, the system I'm talking about is the Boeing 747, a very specific aircraft that will be built and flown and used in a commercial setting. That is the system. Now, models give some abstraction of a subset of that system. And what you need to understand is that it doesn't matter what you build or what you create, unless it is a flyable Boeing 747, what you have built is a model of a 747. Some of the views that can be presented there is like a scale model. Is there any usefulness to having a little scale model of an airplane before you build one? What about a flight simulator that simulates flying a Boeing 747? Is there any value in building one of those before you build the aircraft? I got a strong yes for that. I'm going to tell you, and I know I tell this story a lot because it's one of my favorite projects that I ever did. All right, one of my favorite projects that I ever did was for a company called Audubon Engineering. And what I did was I was very lucky enough to get this contract to take what they do is they build prefabricated oil platforms. Think of like a section of an oil platform that they build and then they push into other oil platforms, right? And so I was lucky enough to get involved, and the engineers had already designed the oil platform. But what I got to do is I got to buy 3 Microsoft HoloLenses, and I imported the CAD drawings, and I went to St. John the Baptist High School outside of La Place, Louisiana, and I went to the gymnasium with these engineers and some operators. And I pulled up an exact scale hologram of the platform that was being built. Of course, you don't see it through the glasses. But the operators got to walk around and look at the hologram. And after the 5 minutes of like, oh my goodness, the alien's going to come. Like, after they sort of settled into the technology, it was so awesome because they had this like 60-year-old operator. This dude's been on an oil platform for 40 years, right? And he's walking around and he's looking. I'll never forget because he had kind of a big belly. He put his hands and doing like this the whole time. And he's walking around. You can't believe it. But then he starts to settle in and he starts looking at pipes. He starts going over. And then he stops at one point. And I see him do this. And of course, because I can't see anything, it's literally doing this. And then he walks over to the engineer and goes, there's a flange up there. There's a flange. Now, I can reach it. He's doing this to the hologram. I can reach it. But that flange needs to be down here. Because if it's here, I can pull on it and I can use my strength. If it's up there, one of two things is going to happen. Somebody that's tall enough is going to yank on it and hurt the flange in downtown, or some young person is going to go up there, hang on one side, and get injured. And so I don't see anything in the pipe. Let's move it down 30 feet. And the engineer goes, and I thought nothing of it. About 5 or 6 other things that they did, but they spent about an hour and a half walking around, and my project was over. They deleted it. Put the HoloLenses into storage, nothing else. I charged them $60,000 for that. I was like, so I talked to my cousin as the vice president. I won't tell you how I got the contract, but my cousin was the vice president. And so I went over there and said, how could that possibly have been worth it? An hour and a half. It only took me a few days to put it together. How could that have been worth it? And he goes, no, you remember that pipe? Because he wanted to come down and hang out and see the cool stuff. So you remember that pipe and that flange? That took me about 30 seconds to change inside of AutoCAD. If we would have been in construction and found it, it would have cost me hundreds of thousands of dollars to make the modification. If we would have deployed it with that, and it led to an injury, or we had to do a repair that led to downtime, it would have cost us millions, right? So having a model of that old platform potentially saved them millions of dollars. There's an incredible amount of value in building models of systems. Little things that you don't think of. What happens if you double the pressure on that old platform? You can test it in a simulation. Do you want to test it on the $8 million platform? No! Then go boom, right? People die. You don't want to do that. So yeah, you get to do that stuff in the model. It's incredibly valuable, all right? So these models represent some subsystem. And it might be that little thing, but hey, that little bitty scale model that we think of as a toy, some aeronautics engineer might look at that and go, you know, these wings won't be able to handle the amount of shear that you would expect. And it might catch something. You never know. Or a salesperson needing to sell it, go, look, this is what it looks like. Have a little scale model of the company thing on the side. There is value in these models. A view is much more focused than that. It looks like a singular tiny aspect of it. For instance, like the wiring diagrams, or maybe the actual blueprints of where the seats are going to be, right? It looks at these very sort of detailed focus. It's a one view. What is the wiring electrical view of this plane? That's what a view is. What does it look like as far as like the structural integrity? Where are the pieces of metal going to go? So those are the sort of things that you get from a view. And models are collections of views. So to show this, it's another diagram. Inside of the system itself, that's the Boeing 747 that we're building. There are two possible views, models. The scale model, but also the flight simulator. The flight simulator probably doesn't need to know about wiring. It probably doesn't need to know about fuel. It probably doesn't need to know about the blueprints if we're going to build out an accurate model. But the scale model, it doesn't care. Now, it might provide some degree of the same view, some degree, but not really. I mean, there's not a whole lot of overlap. So this is how you can build these out, and you can build more and more of an accurate view. What happens if our model is exactly the same as the system? It is a system. We have built a 747, right? That's just all it is. All right, so anyway, that's our examples. Now, we get to transition with the system, which is what we're creating, the model, which is some sort of subset of the things that make up that system, and the views, which are like individual aspects of the system that we can model, to software. And what the UML does is it looks at different ways to break down software into views and models. Now, this diagram does kind of let us know that there's some different views into the system that it looks at. Because the UML is multi-diagrammic, meaning that the UML models a piece of software, right? Looks at all the different subsystems of a piece of software, and it does it by taking multiple views through creating diagrams of those views to create a more large, more extensive model of the system. So it's multi-diagrammic. These diagrams can be split into logical, implementation, process, whatever, I don't care. But look at what slide 7. There's only one question that will come from slide 7. One question: what is the unified view of software? What is the one that's right in the middle? the use case. It is a unifying view within UML, and we're going to talk about that. I bet you a lot of you are super comfortable with that because you've developed in Scrum. And the driving thing inside of Scrum is a user story, which is essentially a use case, right? Essentially a use case. So that's the most important part about slide 7. I'm going to very briefly discuss slide 8. Slide 8, I pulled this from a textbook, and I left it in unaltered because I don't want it to be altered. I accidentally deleted the citation, so I'll try to make sure y'all know which textbook I pulled this from because I need to give credit. It says 80% of what we do can be covered by 20% of UML. No. I have a printout of the UML in my office. It's like 350 pages. You can do the vast majority of your life only using about 10 pages of that, all right? So we're going to cover those 10 pages, not the 20%. We're going to cover the 10 pages. There's a lot there, but we're going to look at a very small subset of the UML. All right. Specifically, the baseline consists of use case diagrams, class diagrams, package diagrams, interaction. I've bolded out the ones that we're going to cover. The use case, the class diagram, and a sequence diagram, which is a type of somewhere between interaction and activity. There's other stuff there that is important, but not necessarily as good to teach. For instance, package diagrams. Now, all of you have been at least exposed to packages. You've had at least one Java error that said error in package so-and-so, and you're like, wait, what? I didn't use a package? What is a package, right? So you've at least seen it. That's kind of important, but outside of the scope of this class. Things like state diagrams. Anybody taking 479 right now? Nobody? All right. It's my first time in 12 years I haven't taught computer science 479, and it's like breaking my heart. I love that class. And one of the central diagrams in 479 is called the finite state machine, or we actually call it deterministic finite automaton there. But those finite state machines are a great way to describe behavior, but many of you will at one point take 479, so I'm going to leave those out of there. That's the other important one. And also eventually deployment diagrams are more and more relevant because some of the stuff that we talk about now is like UML starts to show its age. When we talk about deploying a web app, we're looking at things like AWS CloudFront for sending code to the edge. We're looking at serverless architectures. We're looking at micro, like Kubernetes, these ways to deploy code and serve code. So UML starts to show its age a little bit, but the deployment diagram is a great way to cover that. It's just beyond the scope of this class. We're going to cover the 3: use case, class, and sequence. Okay, so let's move on to a use case. And y'all are going to think I'm crazy because the next slide is going to show a use case. And at the center of the use case, we draw stick figures. All right. Stick figures at the level of first graders, right? On the left-hand side of this slide, you see the first example of a use case diagram. And it consists of 2 primary components. The first is the stick figure, what we call an actor, which is an external entity that interacts with our software. Sometimes this can be an actual, what we think of as an actor, like a person. It can be an administrator, a customer, even be a developer. But it can also be things like a GPS satellite. It can be any of those things. No matter what it is, we draw a stick figure to represent that entity. But what we need that to represent anything from outside of the system itself that will be interacting with the system that we create. The next component is inside the oval. And this oval says purchase ticket. This is the use case. And I know this is a use case diagram, but the oval is the use case. It represents a lot of things inside of it, but it's the activity. We call it something that has a verb in the name, like purchase ticket. Right? So it describes some interaction. So the two together give us a lot of information. What is going to be interacting with our system, and what will it be doing with that interaction? What is the interaction that it's doing? So those things two together kind of give us a set of something we call a use case. So I'm going to talk about actors and use cases, but what you need to know is that we will eventually get past the little ovals, and we'll see a much more relevant and useful part of our use case. So actors, already mentioned exactly what it should be. We draw them no matter what as stick figures. Now, technically, I mentioned it could be a GPS satellite. Okay, you get a little bit of creativity. You can put a little stick figure of a satellite too. That's totally okay. You get a little bit of leeway, but it can even be things like physical environments. I was on a project a few years ago where we built out use cases, and some of the use cases were snow, freezing rain, sleet, heat wave, which was crazy, right? Flood was one of the actors. A flood was an actor, but you kind of see that stuff, right? Now, what's important is that it has a unique name, but it also is very detailed. It can include a description in it. So it doesn't just be my grammar. It doesn't just limit itself to passenger or customer. You probably need a little bit more than that. So you would probably do like customer as the name, and then as the description, you would say something like trying to buy a ticket from Franklinton to Covington or something like that. That's the description. All right, so next up is use cases. Now, the use cases on the visual side are ovals, and they're somewhat limited in their usefulness in the diagramic side, because the only thing you see on the diagram is the unique name that should be descriptive of what happens inside of it. But there are components here that are incredibly important for later in the lecture. They are entry conditions, exit conditions, and the flow of events. It lets us know on the visual side what is the name of it and who participates in that activity. But on the darker, the deeper side of it we're going to cover, it also gives entry conditions, exit conditions, and the sequence of events. So let me show you what that does right here. Slide 13 is our first use case, and I'm going to shut up for a solid 2 minutes and let you read this because there's a lot of text here. All right, we'll say that was 2 minutes. Going back to slide 10. It's the same thing that was at the left side of slide 10. But this gives us a lot more detail. I want you to think about what you just read from two perspectives. The first perspective is a customer that wants something built. What they want built is like a little kiosk, ticket distributor, or something like a subway or metro. I think everybody here has kind of taken a subway at least one point or a train somewhere. That's what they want to have created. And then think about it from the perspective of a developer. Somebody that's actually going to be building out this thing. We know from the name that this is where a customer is going to purchase a ticket. We know that it only involves one entity, and that's the passenger. What is the system that's being built? Yes, it is the distributor itself. That is the system that's being built, is the ticket distributor, all right? So this use case is one look into the functionality of what we're building, which is a ticket distributor, all right? What are the preconditions? the entry conditions. Kevin, read them out for me. Not something we usually see inside of software, is it? Talking about the physical location of where the passenger is going to be. We assume that our users are going to be actually at the page, right? But since this is a physical place, we want to describe exactly what's going on to the best of our ability. Is that for the developer's knowledge? No. It's for the customer's knowledge. All right? We worry about that aspect. Now look at the event flow. Passenger selects the number of zones to be traveled. Distributor displays the amount due. Passenger starts money of at least the amount due, can be more. The distributor returns change, and then the distributor issues a ticket. And what should happen if everything goes right? Pressure has a ticket, aka exit condition. Good. All right. Has anybody ever seen a test case before? You just read one. All right. I know I called that a use case, but think about it. All right. Going on from this. Okay, so let's look. There's a big question in red. Let's ask ourselves a question in red. Is anything missing about this use case? I want to be clear on something. You've only known what a use case is for about 15 minutes. You've only seen one for about 4 minutes. Now I want you to analyze it and tell me if anything's missing. And oh, people in chat, I am reading chat. Like I can see your message if I were talking. So if y'all got an idea. What could possibly be missing? What do you mean? I'm sorry. Can you pull your mask down a little bit so I can hear?
That's the event flow. Things go right, sure, but you know, what if they don't have the money or what if things go wrong?
Doesn't have to. Well, and I'll tell you this. We can assume that they have sufficient money, but what you said right there is perfect because you said, "What happens if things go wrong?" And that's what Justin says.
Yeah, no,
what if they can't go to the zone they want to?
Yeah, zones can be filled, many things, and this list of events that can go wrong at any point. So I mean, that event flow, and hopefully if everything goes right, yeah, it'd be good. But I mean, all that might not go right.
I flew to Seattle a while back for a conference, and they had one of these ticket distributors, and they were asking like, do you need a stop on the blue line or the red line and the green zone or the red line? And all I could think of is I truly believe that marijuana is legal here because I cannot understand what the hell they want, right? I just couldn't figure it out. So I didn't, how many of you really knew what they were talking about with zones? Couldn't that lead to a question? Yeah, you didn't know. So that's awesome. Yeah. Yes. So it could lead to a good conversation, right? Also, you said you didn't really know what to talk about zones? So yeah, wouldn't it lead to a good conversation? Let's talk about it. Would it be better if they selected the station they were going to? Would it be more understandable? And we can have that conversation based on this. I don't see any code here. A customer can understand that. But look at what Justin and Kevin are talking about. They're talking about exceptional cases. They said, oh, something goes wrong. But we can kind of go, since it's an entry condition, we know they have enough money. What happens if the machine ran out of money? Can't give change. I mean, if I just put a 20 in, that matters to me. I don't have that kind of money. Like it's just, so the other things, like what happens if I see that it's going to be a lot of money? I just walk away. How long do you wait? I met the entry conditions, but I didn't get to the post conditions. Things like exceptional cases aren't covered here. But here's what's really interesting about it to me. We've known about this, or we've only seen a use case diagram for about 6 minutes now, and we're talking about what it does and doesn't have. You can talk to a customer with these diagrams, and it can be understood. It can be communicated because it is non-technical. But what is missing? These exceptional cases, all right? So let's look about what we can do with some of these and more that we can do for use cases. So there's a relationship, the extends relationship. Now, I'll be honest, I'm not going to ask you too much about this stuff, but look at what the extensions are. We have a passenger that interacts through the system by purchasing a ticket. This covers the general case, the most common case, but there are extensions of this that represent the extenuating, the special, exceptional events that may happen, things like timeouts, no change. I hate the one out of order, that makes no sense to me. But these things like canceling it out, it's a way that the exit condition can be met. And this is important that we understand all of these cases. For those, we show a line that says this is an extension of it. So now we can see that passengers are the actors, they interact with the use case of purchasing a ticket. And there's all these exceptional cases that extend the other way. There's one more useful thing that I'm going to show on slide 15, and that is the includes relationship. Because it doesn't matter what you're doing with the system, there might be some similarities. Just like in object-oriented programming where we have superclasses, like with some like included functionality of subclasses, here we can have, it doesn't matter if you're purchasing, and once again, I'm sorry for having in Hammond, Louisiana, assuming everybody's going to the subway or taking public transportation before. You can have day passes, you can have single drive passes, you can have a card that has a balance on it where you just use it over and over. There's all these different options. So when you walk up to that ticket distributor, there you go. When you walk up to that ticket distributor, you might be there to purchase single ticket, you might be there to purchase a day pass, but all of those possible interactions do include one similar use case. One similar interaction, and that is what? Collecting the money. They have to allow you to pay. It doesn't matter what you're doing, you do need that collection for money, right? Which also captures Scott's point that there's a form of payment. It gets there. Now, could I do that in one single use case? Absolutely. But here we get to break it into these different, you don't want just the entire event flow to be the text version of code. This lets us break it up into each interaction and sort of sub-edge one of those interactions. This is a very useful use case diagram. Now, the visual side of it has, all of this stuff. How many textual use cases are represented here? How many of those have text in with entry conditions and exit conditions and event flows? How many use cases are in that use case diagram? There are 2 that have direct interaction with the passenger, but there are 5 textual points where we're going to say, here's the entry condition, here's the exit condition, here are the event flows. All right? So it's going to be, and it's kind of tough, and believe me, whoever said 2, good, because you're thinking of it like an object-oriented class. So it's a very good wrong answer. Because what we have here is we have this very specific entry condition here, is that a customer has reached, or sorry, a passenger has reached some point and purchased multi-card and has sufficient funds, right? Now this is the exception case where they didn't meet the entry conditions here. This is the exception case where they didn't meet the exit conditions. But all of them have all of those 5 parts: name, participating actors, entry conditions, flow events, and exit conditions. All of those 5 things have textual use cases behind them. Very good. So slide 16, if you're taking notes or you're at home and you want to just remember something, slide 16 is going to be on the test. I just promise you. Slide 16 is going to be on the test. All right? This is the most important thing because I actually am really, 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 really big on use cases. Not just in class, but I use the heck out of them in real life. And here's why. I'm going to combine points 1 and 2 and say that this is a really useful tool for communicating with clients and developers and everybody in a way that we can elicit better requirements. Elicit is a strong word for pull. It's almost like a demanding of requirements, but it's a little bit different because it's like teasing, right? It's not calling a dog. Here, Buck. And it runs up and jumps on you. It's a little bit more like calling a cat. Kitty, 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 kitty. Yeah, kitty, kitty, kitty. It's almost like that, right? It takes a little bit more work because you want to pull more information from it. That's what elicit requirements means. And you have to meet them where they're at, or at least to compromise. You can't come at them with code. You can't even come at them with the next diagram. You have to come at them with stick figures and ovals. And after you do the stick figures, then you can talk about sets of events, and you can communicate with them in a common language, right? But what we get from it, what we elicit from it, like we do, what we elicit from that, what we pull from it, is a set of requirements that is robust and complete. It describes everything that the system should do. And why is that so important? Why do we know what our system should do at the end? Because I want to get paid. And when am I done? When it does what I said it would do. All right? Remember that meeting where we generated our use cases? My system does all of that. Make the check out to John Burris. Don't worry about the doctor and PhD stuff. It cashes the same. I need to know that, right? I need to know what the system is supposed to do, and so I can generate a test case. Because let's go back to this, slide 13. Somebody tell me the difference between that and a test case. One difference between that and a test case. The only thing is the word use in the title that's different from a test case. If I wanted to test, and this is called a functional test. If I wanted to run a functional test of my system at the end, all I do is I go, well, we're going to call this the purchase ticket test. And the participating person is going to be, I'm going to be a passenger, and I'm going to have money, and I'm going to walk up to my system, and I'm going to do that event flow, and I'm going to check and see if the exit condition is true. That is a test case. A test case has a name, participating actors, entry, exit condition, and event flow. That is a test case. I promise you, it's a functional test case. That is a great question. What is the difference? Use cases is what we call them at the beginning. Test cases is what we call them at the end. And it's that easy. And it's crazy. And that's why I love slide 16 so much. It is a unifying document. It's in the middle. Because from the very second I learn about a system, I start generating use cases that drive everything. And if you're using Scrum, these use cases become user stories. And that drives every second of development all the way down to the test case. From the beginning to the end, a use case allows us to develop software. And I couldn't tell you the difference between a use case and a test case besides, have we started coding yet? Then it's a use case. All right, which is incredibly useful. Slide 16 says that I can elicit and communicate better requirements with the customer. Remember, I combined the first two. Scott, Kevin asked, what is the difference between a use case and a test case? And all I can come up with is test case is what we call it at the end. All right, so it lets us to communicate in a way where we meet customers at an easy place and elicit better requirements. And then by having us have the same thing between driving design and test cases, it unifies everything. It just pulls it all together in one nice package. Use cases are incredibly useful like that. So be honest. A lot of you are in 411 right now. Have you thought about using use cases in the software you create? Do you think you might? There you go. At least it's tempting. That's what I wanted. At least a tempting thing that maybe this is useful. All right. So any questions about use cases? I hate slide 17. That's not the way I teach. So in summary, use cases represent some external behavior of your system. It provides the meat of the model. Whatever. I can't stand this slide. Why do we use use cases? Somebody tell me, why do we use use cases? I know I just said it, but say it back to me. Anybody? Good. Good enough. We need to know how people interact with our system. Be good. Mm-hmm.
Explain every part of the project, explain
So for those at home, Kevin just said that it's good to know, have more understanding, because he just took on a project at work where the first thing he did is he had a phone call and they explained the project to him. So before he would understand it. So this definitely, I'll go back off of that one and say, you know, we have to be careful because we don't want to do ad hoc software development. Ad hoc is kind of like as we go, making decisions. And has anybody ever been waist deep into a software project and realized you forgot something? Yeah, at least Kevin's admitting to it. Megan did too. And it's kind of hard to like retcon it to like, oh, yeah, we just do this stuff. And yeah, it starts to be a challenge just to make it fit retroactively. And what that ad hoc, it leads to kludges. Have you ever used the word kludge in software? Man, I hate that I'm the one in it. Kludge is not a complimentary adjective. It is not. Kludgy means dirty. It means quick. It means, what do they call it? Rednecking it or something like that. Like you use duct tape, you know, just to fix something up. It's just crazy, all right? We try to avoid those things, and use cases can do that. Lindsay.
How, in a corporate environment, how helpful is it that your process mapping team gives you, or not a UML, but a process map? And then you just remake the whole thing.
It's somewhat common, especially in delivery centers that focus on digital transformations, because this is what they live on. They don't get to technical. I mean, a technical person probably won't even visit an office. Instead, they have these people that come out and they look at core business processes and then map it out in a way. Yeah, thanks, Justin. So yeah, map it out in a way that it makes sense to the customer first, and then they pull it into a Scrum team. And the Scrum team will sit there and they'll make that into a user story and then drive from the user story. So that is very common, and that's what you get with IBM, DXC, CGI, those big development houses. DXC and IBM, I think they have the word delivery center in their things, and so that's what they do is they look at digital transformations, and it's all built off those processes.
That's what I was wondering, because my current boss, every time they're remaking the process, like they make a UML after.
Oh yeah.
It's very important to read it, so the work.
Absolutely, incredibly important. All right, so the next one. Class diagrams. You have all seen a class diagram. Even if you don't know it, you've at least seen a class diagram. It may not have been called that, but in 280, we talked about it. Class diagrams give a static structural view of the system. And the most important, the single most important, that is not in the slides, but something that I want to make sure to you is important, is there's a one-to-one relationship between a class diagram and the code that it diagrams. A one-to-one relationship. Static means it will never change. You don't show any behavior of the system. But it shows the attributes and operations of all the classes that we design. Now, I'm going to show this in the next slide. But attributes and operations, you might have heard as state and behavior in 280, or member variables and member functions in 280, right? So I told you, we're going to get a lot of 280 in this class. We're going to be rehashing it over and over again. But it's really, really good. It's a way to sort of describe each individual component, because we're looking at the structure of it instead of the use case side of it. So let's talk about it in a little bit more detail. Class diagrams show three different perspectives of software. Even though we're looking at the structure, there's still the conceptual side of it, where we talk about what a class should be and contain, and what other classes there's a relationship with. Now here's what's crazy. There are 2 points here. The first is language independent, which means that it doesn't matter whether or not it's Java or C#, it works either way. The first point, going back to it though, is bananas, all right? It says that it should also be software independent. Now, sometimes this means like the case tool, like the thing that you're like, did you use Draw.io to draw that? No, that's not what I really mean. What I really mean is that it should be independent of the software you're designing for. I'm going to throw this back to 390, all right? In 390, you used a linked list when you were implementing a class. But then the next one, you had to implement a queue. Did you just completely rebuild your linked list, or did you use code reuse, right? You copied and pasted the linked list class, and then you built out your queue. So when you build out these classes, they should be useful regardless of the software you're building. Have you ever written a really nice class that was like a database wrapper or something, and you spent so much time on it, it looked really good, so you like saved it for another project? You totally will. You totally will at some point. And you get to reuse those really good snippets of code. And so this is independent of even the software that you're creating. The second, this is good for specification. Now, in a class like 285, the easiest way to divvy up work is you do front end, you do back end, you do the database, you do our documentation, and never be the documentation person. All right. So that's the easiest way because it kind of separates everybody's fear in a way but eventually your software for that model side of it, the person that was doing the back end work, the logic of the system, is too expansive for that. So you can actually split it out by individual classes. And with a class diagram, you can give them enough information that they can say, hey, you write the database interface, and then you handle the customer integration. And one developer can work on the database interface, and the other one can work on customer integration. And if you specify it well enough, when they're both done, it'll just work. You won't spend a lot of time on integration. So a class diagram also specifies enough of the interface that once two people kind of split out work, it can come together. And then finally is implementation. Did you know that even JGraph has UML support? Some of y'all might not know what JGraph is. It was like the cheap Java IDE that's like free that we used to use in 161, right? But Eclipse, IntelliJ, you can do generate documentation UML, and it'll generate the class diagrams of whatever it is that you create. It's one-to-one. It's really cool. So here's your first example. Don't look at the one on the left, look at the one on the right. All right? A class in code represents a concept. All right? A concept of what a student is. All right? Now, one thing that's important is we decide what state and behavior define a student. Now, if I were talking about Kevin, he's not a class, right? He's not a type of person. He's a person. He's an instantiation. So a class is an abstraction. An abstraction that is not just Kevin, but also all San Quiz and watch everybody else in front of her. So it's going to be called out the entire semester. That same class needs to describe all of these specific instances. Right? And it describes it from the state and behavior, member variables, member functions, attributes, operations. Whatever words you use, it has all of those three things: the name, the attributes, and the operations. From there, we put as much information we need to write out the basics of code. So on the top right-hand side, you see a very basic one. The name of the class is tariff schedule. The very first, this is one big rectangle with three smaller rectangles. The top one always has the name, it's the easiest one. All right. The second one has the member variables. And this one has one member variable called zone to price, and the return type is table, a complex type because it's capital T. There are two member functions, get zones and get price. They have method signatures for the member functions, which give us our return type, our parameters. And on the first actual class diagram that you're going to see on the next page, it's going to give us modifiers as well. Have you ever seen a class diagram now that you've seen one? 280, did y'all have something similar like this? All right, good. Just about everybody's at least seen one. So let's see an actual class diagram. Every class diagram has three parts of one big rectangle. The class name has to be unique, of course. I mean, software, you can't have repeated class names. Should have the member variables, should have the member functions. So let's look at this class diagram on the bottom. On the left-hand side, you'll see minus, plus, and hash. The minus is private. The plus means that it's public. The hash, or the octothorpe, or the pound sign, whatever you want to call it, represents protected, which I don't even remember what it does because I never use it. And then static, it'll be underlined, but we'll get more on that later. It's an abstract class, the name is going to be attached. I don't care about all that stuff. What I care about is that we can understand the bottom. We have an employee class. How many member variables does this employee class have? The first one, Lorenzo answered 3, I'm sorry, which is correct. The first one is name, the type is string, and is a private member variable. The second one, what is the name of the second member variable? ID, awesome. So I don't need to go on and on about it. The type is long. How many member functions does it have? 3. All right, now we've got entire signatures here. Okay, the return type is written a little different in here, but we have a public function named getName, type is string. Now that's the return type. On the third member variable, you can see the way that it's written here. Written here, we have a private function called calculate internal stuff that doesn't have a return type, and it has 2 parameters, type byte and decimal. So I'm about to do something. Now, this ain't 161, so y'all understand I'm writing on a crappy Dell keyboard. It's like the non-clicky, no tactile response. These are the worst keyboards ever made. They're very quiet, which I don't need. If I make a mistake, y'all don't call me out on it too quick. Let's see. What I'm going to do is right now in Java, I'm going to create this. All right. Now, assuming what we normally assume, we have a class called employee. Right? Basic stuff. I have no creativity there. All right. That's what it is. According to the specification, that's what it is. Now, I have one member variable. It is private. The type is string. Now I do have to change it to capital S so that it meets my language. But it was always going to be a string. So that's okay. I'm not cheating here. Now, here's where I get a little bit of creativity. Normally with naming conventions, I would make it a lowercase n. But I'm going to follow it exactly here. I'm going to make it a capital N. All right. I'm going to follow the specification that the designer used. I'm going to make it a capital N. All right, so the next one, if I'm going down this same class, I see another variable. Now, I'm not going to write the word public. Why? It's a public class. Good job, Cindy. So I'm not going to do that. I'm just going to do a long and call it ID. The next one, they protected, which I'm assuming in Java is the word protected. And it's double the name salary. 1-to-1. When you understand that the ID inherits public from the class, 1-to-1. No creativity needed. All right. So a couple of member variables. It's public get name. For some reason, we might modify it on this, so I'm just going to do it. Return type is string. Name is get name. No parameters. I'm just going to go ahead and put some curly braces and some semicolons there. The next function is set name. This one is public as well. It doesn't have a return type. So it can do this. Since I know Java, there's no assumed return type, so I have to add void there. Not cheating. Okay, it's not cheating. I'm making that. There's only one way to do that in Java. It's still 1-to-1. Okay, it's still 1-to-1. Okay, and the last one. I can do the final method, and I can make this one private because it starts with a dash there. And the return type is going to be void again. It says calc internal stuff. Now it says that there's two variables coming in, a byte called X and a decimal called Y. I don't think Java has a byte, does it? I think it calls it like short or something. I don't know, but I'm going to do my best here. I'm going to say short X. Decimal, that's probably like a decimal number. I don't know. Let's try int Y. And we're doing our best here, what we've been given. And now we have what's called the skeleton of our class. The skeleton. Really cool things about this. First, that it's one-to-one. What's represented in that, y'all, you can put it in a lot of pieces of software. You can make the class diagram and hit generate, and it will automatically generate this to you. Does this mean you're done? No, what's it missing? Yeah, meat. All right? You're not skeletons. Your skeleton's wrapped in meat. All right? It needs the meat. The meat is important. All right? It needs those functions filled out. So it's not like we're done. But what's really cool about this? When somebody else needs to use this class, do they need to know what's inside of those functions? This has everything you need to do. You need to interact with this class. You know what member variables it has. You know the externally accessible points. Now, there's some other things here, like it has kind of an assumed constructor, which maybe we need to think about which language we're using, whether or not we want to use a default constructor, stuff like that. But this gets us there. There's something cool about this. The designer, the engineer, the software engineer built what's on the left-hand side, and the developer started with what's on the right-hand side. But there's already an error in this code. There's already an error in this code. Does anybody see it? It's a logic error, not a syntax error, a logic error. Don't snap. Good. You know what? Actually, Justin, that's on me. I think from a design perspective, I should have had return name here because I should have understood. That's actually my fault. I probably should have had that there. To have a full skeleton, I would have needed that. So, yeah, you are correct. That's probably more on me instead of the designer, though. That's kind of my error. That, but very, very good point. Wait, one more time.
If you're setting a name, normally you need a name, but that's the same as the UML. So.
Getters and setters. Getters don't have a parameter and have a return type. Setters don't have a return type, but they do have a parameter. Once you're looking for it, it just hits you wrong, doesn't it? Like it's missing it. All you did with getters and setters kind of got caught there. So we can see this now and we can make this change. And more than likely, I would need to put in a string. And here, I can even fill this in the same way that Justin pointed out. I can go ahead and return the name with the getter. I can do this as well with something like this. Because I know that I can fill in that functionality. We can already start to look things just at the design level. We can look for errors that might rear its ugly head inside of code. I'm not going to fix that on the PowerPoint because that's the same thing I use all the time. It's a very intentional error. So, any questions about this?
Would get name also take in name as well?
No, usually you would want that to be like a getter and a setter is an external interface to a member variable. So if like way down here you had like inside the main method, you had employee Charlene with new employee. I cannot type on this damn keyboard. What you have is instead of doing something like this, you can't really do that because it's a private. So the way that you would want to do it is you would want to do this. And then you would have something like this. And the reason why you wouldn't want a parameter is which object you're calling it.
It just makes sense now. I see. Okay.
Awesome. Very good. Awesome. Very good.
I feel dumb.
No, don't feel dumb. Dude, 280 was 2 years ago. It was 3 years ago. Don't worry about that stuff. We're going to, if I ask right now for anybody to define the word polymorphism, I don't think I'd get many answers. So it's okay. We're good. Oh, yeah, and also 280 is vastly different experiences for a lot of people. Any questions? All right. So there are 3 types of relationships between classes. See, these class diagrams have more than just that one square. What makes them useful is when there's a lot of those rectangles around. And we want to know what all of these classes do, like employee, manager, retail, whatever it is. So I should have come up with a better example off the top of my head, but I can't. So student worker, faculty, administrative assistant. How they interact is very important with each other. And there's 3 primary types, 2 of which I care about a lot, and one as long as we're talking about it. Okay, the first is association, which is when 2 classes need to know about each other. The second is aggregation, where one class has a collection of another class. And the third is super important because if we had like a traditional 280, it'd be like shape, there'd be circle and square. Or animal, there'd be dog and cat, right? What is the relationship between a cat and an animal? Inheritance. It is a superclass subclass relationship, all right? And I know it's been a while, but we'll make sure that we get that. So here's what it looks like. Very important point. Slide 23 and 24 both represent a relationship called association on a class diagram. Now there's binary association, which means that both classes need to know about each other. And then there's unary association. I think I say it the country way with unary, but that's the way I've always learned it. So there's unary association that only goes in one direction. I don't care. Just binary associations. Just draw a line, all right, between the 2. But I want to show you what this looks like. If class A and class B are being developed, all right, this is an association relationship that you see in front of you. And you can almost tell by the classes themselves whether or not they need to be associated with each other. Because A has a single member variable. What is that member variable? The class A has a single member variable. What is it? It's super tiny. Let me zoom in. My B is its single member variable. B has one member variable. What is it? My A. So when I'm implementing class B, I have a member variable that's typed as A. When I'm implementing A, I have a member variable that's typed as B. In other words, in order for A to work, it needs to know what the heck a B is. For B to work, it needs to know what an A is. I want to give you an example of how you can remember this in a pretty straightforward way. In C++, your A.cpp needs to have an include B.h, right? I don't know if y'all does that hit me? Y'all use C++ enough to use the include and all that? No? Oh, dang it, that would have been a great example for people to see. Gotcha. Gotcha. Well, let me put it this way. When you've got Eclipse, or if you have to, IntelliJ open, and you have a.java in there, it isn't going to work unless you have a b.java in the same folder, right? Because it has to see B, right? If you have b.java, it will have a.java in the same folder because it has to know about it. It doesn't matter if it's two directions or just one. All right, so Justin, you got the C++ reference. I'm glad. All right, so it doesn't matter if it's two directions or just one. Don't worry about this slide with that whole unfilled arrow. Don't use it. Just straight arrows is fine by me. All right, aggregation, I don't want to talk about this too much. Aggregation is when one class has a collection of another class. So on the left-hand side, you see a crate. And the crate has a private member variable that is in a, and I'm sorry, I'm not really sure how C# writes this, so in C++ it'd be a little bit more clear. It has an array of modules called a module. And that array contains multiple modules. I don't care about this. I do not care about this. This is not super important. But if you happen to see it, the only thing I want you to know about this is a crate has modules, right? A crate has modules, all right? And the last one is inheritance. Now this one's we're super clear on. It's an is-a relationship. And in this case, you have a base class and a derived class. You've got class A that has a member variable and two member functions, and class B that has just one member function. In this case, B is a subclass. So it's going to be public class B extends, oh shoot, is that the Java word? Dang it, is it extends? Yeah, extends A. Yeah. I've been writing in Python for like a year. It's amazing how quickly you atrophy on other languages. Anyway, so A is the superclass, B is the subclass. A is the base class, B is the derived class. B inherits from A, whatever you want to say. Now I'm going to have to ask you a very tricky question. This is a trick question, and I'm telling you it's a trick question before I ask you. If I have a variable of type B, does it have a member variable called myX? I'm going to write this out so you can see it. Why do I keep hitting Windows E? If I had a member variable called B my variable, and I did I should have chosen something smaller. My X. Does it work? What's that?
I think so.
We have one thumbs up.
It works.
Scott says it works. Confident. Lorenzo was like, think so. Scott was like, it works. All right. The way it works is this way. See, if I said, does B have a member variable called myX? You want to say no because, look, it doesn't have one. But it is inherited from its superclass. So it does. It comes, like, that's what inheritance means. You can theoretically or logically or whatever visually you can do, take all the member variables that are inside of A and copy and paste them inside of B. That's what inheritance does, right? It inherits down to the subclass. And that's why when you're in the class B, it has those variables inherited into it. This is the one I think we're the most comfortable with out of the different relationships. And it has the open arrow. The only thing that's crazy about it is it's hierarchical. And we like to think the arrow should go down, but it actually points up to the superclass. Subclass and the arrows go up to the superclass. The way I remember this is because usually when we draw inheritance relationships, it looks like a Christmas tree. And so I want the points of the arrows to look like the Christmas trees. I don't want them pointing downwards or anything like that, all right? If you need a Triforce of Wisdom example, I can also come up with that too. I'm totally comfortable working in the Zeldaverse, all right? But whatever it is, it should look like a triangle going up to that superclass, all right? Any questions? When we come back on Thursday, we are going to start 2 slides from here. And I'm going to show you this diagram. And I'm going to ask you to interpret it. We're going to understand the structure of a system that doesn't exist. I'm going to ask you functional questions about it. And you're going to look at the diagram and you're going to answer them for me. All right? The coolest thing from class diagrams, it is one-to-one. No confusion. One-to-one relationship. All right, that's it for today. I will see y'all on Thursday.
Dr. Burrs, I had a question about the certifications,
Mm-hmm.
the AWS one specifically.
Yeah.
Is that on like Southeastern's website or anything like that where we have to go through?
Yeah, it's going to be, well, once I get that out, it'll be, it'll be on a sheet, but yeah, so the only thing you have to go through Southeastern for is to get vouchers and then reimbursements. And you do that through a program called WTI, which is WTI@southeastern.edu. And they just send you a check and it gets applied to your account.
So does the student pay for it up front and then it's vouchers or
Yeah, the student would pay up front and then get reimbursed.
okay.
Yeah.
You might notice, do I have to fill out all my paperwork again for 2 years?